Hello, class. I have been putting together a quite a good lecture, and in fact, I made a decision that I am going to replace one of the lectures, the one with the op amps on integration and differentiation, with another lecture on capacitors and inductors. So we're going to have three lectures on capacitors and inductors. This lecture that you're having today may be one of the most important lectures that you're ever going to have in your engineering career. It might be one of the most important lectures whose concepts you take from this lecture and will separate you from other electrical engineers with a physical, conceptual understanding of what's going on in the energy storage inside capacitors and stored in the magnetic fields of inductors. That's one thing I want to put forward right away, is that this is a really important lecture. This and the next lecture, I'll see how much we can get done. I've got my timer on and everything. But as far as conceptual physical science underpinnings of what's really going on in capacitors and inductors, I'm going to teach that to you now. All right. A lot of electrical engineers don't even truly understand what is going on at the physics level inside capacitors and inductors. They just know it at the engineering level, and I want to teach you. Now, another thing that I wanted to do was I wanted to go through and I wanted to finish up, and that's another reason I'm taking, that differentiator and integrator lecture away from the op amps and putting it back onto the capacitors and inductors. We need a little more time on that. Now, before we do that, I want to finish off, just like I said I was going to in the next lecture, I want to finish off that analysis of the difference amplifier that we had. And in fact, let me draw that difference amplifier again. V out, right? Positive or non-inverting and inverting inputs. I take this one, I go to ground with it, right? That's R4. And then I have another resistor here, right? That's going to be hitched up to V2. I'll actually draw, I'll just say V2, right? Everybody knows it's a DC voltage that's going to be fed in there, and this is going to be R3. And then I have another input, right? And this is going to be R1, and this is going to be V1 going in, and I have a feedback resistor on that loop, right? So this is going to be we're going to put R2. All right, does everybody see that's the difference amplifier? Now, to prove that R1 over R2 has to equal R3 over R4, right? That's the only condition, by the way, and that's the condition that comes out of this analysis of node B. Now, in your book, they took about 6 steps, and voila, there they were with the finished product. And I hate that when they do that in engineering textbooks, because you're thinking, well, how did they get from that step to this other step down here? Well, I'm going to show you, because it's algebra, and it's interesting to see how, what they were using. So if we analyze this right here, we know that the current, right, that's flowing through here is going that way. There's no current that's actually going into the non-inverting input of the op amp, right, because it's super high, infinite resistance, so nothing goes in there. So we've got V2 minus V sub B over R3 equals VB minus 0 over R4. And we already had that. That was in your book too. So when we expand this out, right, so I've got V sub B over R4. I've just taking that, leaving it on the other side here. I'm bringing the V sub B over R3, which is negative, over to this side. So that makes it a positive V sub B over R3. And then on the other side, what am I left with? I'm left with V sub 2 over R3, right? And now, if I was to take V sub B out of there, which I have, I've got 1 over R4, R sub 4, plus 1 over R sub 3. And these are all the steps that go from here down to here, right? You can see that basically they went from this point here all the way down to this point here and left out all of these steps in between. And I think it's important to see how they did this. Now, all I'm doing is you can see 1 over R4 plus 1 over R3. If I made both of those R4, wait a second, what am I doing? Yeah, V sub B, take that out of there, and I have 1 over R4. So, yeah, so that is R3 plus R4, so that's R3 plus R4 over R4, and of course that's what this one would be to, where did I get that? V2 over R3, so R3 then comes up into the numerators, so R3. Actually, that works out. I'll let you, do that, but you can see now. If that's V sub B, we know V sub B and V sub A have got to be the same, right? Because that's what an op amp is doing. It's trying to get these to always be the same, isn't it? So if I substitute V sub B back in for V sub A, I end up getting this relatively complicated looking equation, right? And then I just expand this out. I think everybody can see what I've done here. I'm still keeping the R2 minus R2 over R1 V1. That's always the same, but what I'm doing is I'm simplifying this expression that I've got over here into V2. And then I take this a step further because I've got R4 as a common multiplicand in that, so I could take that out. And then on the bottom, I've got R1 times R3 plus R1 times R4, right? V2 minus R2 over R1. From this point here, I'm going to let you do one more algebraic step that takes you to the next equation. It separates out R2 over R1, R2 over R1 here. And you can see that. I'm sure that you can do it yourself. And that gets you to the point that they then say, hey, if V1 equals V2, so V1 minus V2 equals 0, so that means the output is going to be 0. So if we substitute in 0 for the output, and we substitute, we say that V2 and V1 are going to be equal, so they cancel out. I can take this to the other side of the equation, right? And then I've got this one, so we know that those two are going to be the same. The V1, the V2 cancel out. And what we end up getting is we end up getting the relationship. And this is not saying they have to be, R1 has to equal R3, right? And R2 has to equal R4. That's not what it's saying. What it is saying is that the ratio of R1 to R2 has to equal the ratio of R3 to R4. That's all it's saying. It's not saying R1 has to equal R2 and R4 has to equal R2, but that's usually how you set up a difference amplifier, so that those two are exactly the same, right? That's the difference amplifier. Now, what we end up getting out if we use that identity is we end up getting out, or getting our equation that says that V out equals R2 over R1 times V2 minus V1, right? Now, if R2 and R1 are the same, if that's 1,000 ohms and that's 1,000 ohms, and that's 10,000 ohms, and that's 10,000 ohms because it's just the ratio, right, that we're looking at. I could use a 1,000 ohm and a 1,000 ohm here. I could use a 1,500 ohm and a 1,500 ohm here. It would still work out fine, right? But if I did make those equal, if R1 and R2 are equal to one another, and R3 and R4 are obviously then, due to this requirement, are going to be equal to one another, then I could make a subtraction, right? So V out is just going to be V2 minus V1. But what if I did want to amplify the difference? Well, then I could keep R2. Let's say R2 is 10,000 ohms and R1 is 1,000 ohms, right? And let's say that down here, this is 1,000 ohms and this is 100 ohms. You see what I'm saying? We got to keep them in the same ratio. Then I would get 10 times the difference, wouldn't I? Does everyone see that? So I wanted to bring that up and finish that off first. And then the second thing I want to do is I want to start talking about capacitors. And I want to start talking about how do capacitors work. I find so many students. I find students even at the senior level that really don't actually understand how I store energy in an electric field. That's what a capacitor is. A capacitor is an electric field where I store energy. Little sip of some nice hot tea there. What can I? Yeah, there we go. I got a little thing there. I can cover that. Probably filled with COVID-19. So here's what I want to do. Here's what the first thing that I want to teach you is a little circuit like this. I've got a switch, right? I've got a switch and I'll put a resistor in there. And then I've got a capacitor here. There's my capacitor. In fact, the way that they draw the capacitor is to make it look like an electric field, right? Do you see anything touching each other there? No, it's like it's broken, isn't it? In fact, if I was to look at a capacitor, I'm going to draw it out here in a three-dimensional form. So let's say that I have a capacitor. Usually this is a copper sheet, right? And then I've got another copper sheet here separated by a certain distance. Now what fills the void in between those two, right? The void in between these two is filled with a dielectric, isn't it? When I say dielectric, you probably think insulator, right? Most things that are dielectrics also are insulators. Not all of them, but many things. But there's no electrons that are traveling through here, right? Think of this. This is a dielectric. And why do we put a dielectric in between the two plates? Let's say that this is at, I don't know, 100 volts, right? Plus 100 volts. And then the other side over here is at 0 volts, right? It's connected to ground or whatever. So I've got 100 volts across there, don't I? And I've got this dielectric in here. And what does the dielectric do? The dielectric, not all insulators are dielectrics, by the way. But the dielectric is a material, could be mica, could be barium strontium titanate, could be glass, could be air. There's a whole bunch. Could be epoxy, right? We could be looking at a strip, a microstrip transmission line across a printed circuit board, right? So there's a lot of things that we could look at for the electrical field. Now, how does the electrical field actually look in here? Well, the electrical field always starts with the 100 volts, and it always goes to the 0 volts. So my electric field would look like this, right? Always just like current, always from the positive to the negative. And then, of course, I've got a wire coming off here, and I've got another wire going off here. Maybe that's going to ground or whatever. And this is going to the rest of the circuit. So I have an electric field. I'm going to ask you something. I'm going to tell you something, but I'm going to ask you to see how intuitive you understand. Let's say that I have a power supply here, right? Got a power supply there, and 50 volts. I'm just making it 50 volts. Could be any voltage, but I'm just making it 50 volts, so it seems like a relatively large voltage that we're talking about, right? Now I'm going to close that switch. When I close that switch, is current going to flow? When I close that switch, I better give this a value. Let's say that that's 100 ohms, that resistor. When I throw that switch, is current going to flow? Or, because I don't have, there's nothing connecting this. This is an insulator between these two copper plates here, right? No electrons ever flow across that dielectric. Let's write that. No electrons ever flow across the dielectric. No electrons ever flow across the dielectric. There's probably some electrical engineers that do not even know that, do not really understand the physics behind a capacitor, and that we're storing energy in the electric field, right? So you're probably saying, well, when he throws that switch, what's the current going to look like? What is our maximum current? Our maximum current, I don't even have to write Ohm's law anymore, is it? Is going to be V over R. So our maximum current is going to be 50 volts divided by 100 ohms. That's 0.5 amps, isn't it? When I throw that switch, let's just get a little thing here. When I throw that switch, this is going to be time, and this is going to be current in the circuit. My line current when I throw that switch. Now, right now, the capacitor is uncharged. Let's put that way. The capacitor is uncharged. When I throw that switch, what's the current going to look like? Let's say that the maximum current right here is 0.5 amps. When I throw that switch at t equals 0, this point right here is t equals 0 plus, right? So it's just after time 0. It is time 0. Think of it that way. And then we're looking at it as time goes by. What is the current going to look like? Does the current, when I throw that switch, does the current stay 0.5 amps and just stays 0.5 amps forever? Does it start at 0.5 amps? Or does it start at 0 amps and then go up to 0.5 amps? When I throw that switch originally, does this look like an open circuit? Or does it look like a short circuit? I know you're scratching your heads, a lot of you anyway, maybe not all of you. Maybe a lot of you already understand what goes on with a capacitor. But that's what this course is about, isn't it? It's about homogenizing and making sure that everybody knows the same things, and those are all the truth about electrical engineering, right? When I throw that switch I'm going to write this in a box, at T equals 0 plus. Put a box around this. I equals 0.5 amps. That's right. Starts as a short circuit. Capacitors starts as short circuit, ends as open circuit. Capacitor starts as a short circuit, ends as an open circuit. So the way that this would look, if I was looking at the current, the way it would look is like this. Right? And eventually it's going to get down to an open circuit. Right? The current is going to go down. What does the voltage look like? The voltage across the capacitor. Let's draw that. So this is the voltage across the capacitor. And when I say voltage across the capacitor, I'm looking at the voltage across the capacitor, right? So what is my voltage, V sub C, from one side of the capacitor to the other side of the capacitor? It starts as a short circuit, right? So if the capacitor is a short circuit, now let's just find another short circuit. How about right here and right here? What are the voltage differences going to be there in that short circuit? It's going to be the same voltage here as it is here, right? Sure. So if this is a short circuit, if it starts off as a short circuit, there's not going to be any voltage across there, is there? So it's going to start down here at V equals 0. It's going to start down there at V equals 0, and then what happens is it's going to asymptote off at a certain level, right? So the current, the line current, which is the current going through the thing too, that would be equal to the current going through the capacitor, is going to start off as a short circuit and go to an open circuit. The voltage, on the other hand, is going to start off as a short circuit, right, and go to an open circuit. Now, what is that voltage that it's going to asymptote out at? It's going to asymptote out at 50 volts, isn't it? That's a 50. 50 volts, because eventually it's going to be an open circuit. Put a star next to that. That's a star. Now, how does that happen? That's what we really want. How does that happen? What is really going on inside this circuit? I'm going to show you what's really going on. All right. As soon, let's just look at this. Now, copper, billions of electrons, doesn't it? Billions of electrons floating around inside copper. That's why when we use a very short piece of copper wire, let's say I've got a little piece of copper wire here, the electron that goes in that end, even if this is only like 3 inches long, the electron that goes in that end takes almost an hour to come out the other end, doesn't it? Right? If I tagged that electron and said, hey, that electron's my tag, I'm going to follow that electron. Let's say I had an instrument that could do that. I'm going to follow that electron all the way through here. It hitting another electron, bouncing that electron free, you know. So if we had just 1 volt on this side and 0 volts on this side, and I had a current that was flowing through this way. Of course, the electrons are flowing through the opposite direction, right? In fact, I should switch this around, because if I've drawn the electron going in there, I should follow electron flow, and that would be the 0 volt, and this would be the 1 volt. I hate to confuse people, but electron flows in the opposite direction of current. That would be my 0, that would be my 1 volt, and my current, my electrons would be going through that way, and my current would be going back through that way, because electron flow and current flow are in the opposite directions. We didn't realize that charge transfer was dependent upon a negative particle. We thought that it was dependent upon a positive particle, and so that's why we defined current going the wrong way, because we didn't truly understand electricity when we were defining current in the first place. Again, the only reason I'm mentioning this, and that it takes like an hour, you know, for that electron to go through here, is because that's what I'm saying. We've got a bunch of electrons just floating around, free electrons floating around inside copper, huge amounts of free electrons floating around inside copper. And those electrons can easily be knocked out of the valence band and into the conduction band, right? Okay, now let's look at this at this circuit in a little more detail. If I have that 50 volt source, right? And oh, better put that resistor in there. And it goes down to my capacitor, right? Now let's look at instantaneously. Let's look at t equals 0 plus, right? A microsecond, a femtosecond after I throw that switch. Now we have a circuit, don't we? I've thrown the switch. In fact, I've thrown the switch so that it wouldn't be up there anymore. So it's now a circuit. It's still an uncharged capacitor. But what's going to happen? Now, this is the positive side, right? So this is the positive side, and this is the negative side. So right now, this side of the capacitor is attached to a positive 50 volts. And this side of the capacitor, right, is attached to 0 volts. So 0 volts and 50 volts. Now, what's going to happen to the electrons in this plate, this copper plate over on the other side? Remember that we got 2 copper plates here. We got a copper plate here, and we've got another copper plate over here, right? Let's just give that some width, maybe, and maybe you can see it better that way. So we've got a copper plate on both sides, and so all of a sudden, all of the electrons, the free electrons that are in here, aren't they going to want to go this way? Right, so my electrons are attracted to the opposite charge, right? So I've got electrons here, and these electrons are shooting as fast as they can toward that positive 50 volts. They're shooting in that direction. Now, if they're going in that direction, right, all my electrons, which direction is the current flowing in? Didn't I say that the current flows in the opposite direction of the electrons? So the current is going to be flowing this way. And in fact, we're now depopulating the electrons, the free electrons from this plate. We're taking more and more free electrons that happen to be sitting around, and they are rushing toward that 50 volts. Now down here, I've got a negative, don't I? So on this side, what's happening? Wouldn't the positive charges, right, be running toward here? Or I should say that the electrons are heading toward, the electrons from here are now heading toward this more positive side, because I've got electrons here, I've got a negative thing here. These electrons are heading over here. right? Let's just give it a little arrow. So these electrons are heading that way. These electrons at a hyperspeed are heading this way, aren't they? Yep. Because this is being depopulated. If we look at what's going on inside, let's just look at that at that capacitor, blow that capacitor up a little bit, and look what's going on inside. So the electrons are leaving this side, and the electrons are coming into this side. They're arriving at this side. So what's really, so I'm going to have negative over here. I'm going to have a negative charge over on this side eventually, and I'm going to have a positive charge over here because all the electrons left here. So all that's left is the positive charge, right? And on this side, all that's left is the negative charge. Has any electron ever crossed the dielectric insulator boundary in between the two? No, it never has. It's never done that. But this is also like filling up a bottle from the bottom. Let's say that I had a bottle, right? I'll just make like a wine bottle or something. Let's say I had a bottle. I cannot draw very well. And I'm filling it up with water from the bottom, right? And let's say that it's sort of in water. So, and I've got water that's filling it up from the bottom, and it's starting to fill up. Now, what would happen with that? It's not like pouring water into a gallon jug, is it? Where the air can evaporate, or the air can escape, I should say. What's happening in here is the air is getting smaller, smaller, smaller. So I'm going to have more pressure, right? And in fact, if I keep filling this up, aren't I going to keep getting a force working against me? So that I never will be able to entirely fill that, because as I'm increasing filling that bottle, right, the pressure inside the bottle is going to go up. Let's look at the ideal gas law. PV equals MRT, right? The ideal gas law tells us PV equals MRT. I can write it like this, though. P equals MRT over V, right? So look at, as the volume decreases, the pressure is going to increase, right? As the volume decreases, that's going to, it's in the denominator, so that's going to make the fraction increase, and it's going to make pressure increase. And that just is intuitive, isn't it? So as I pump more water in here and that gets smaller and smaller, the pressure, the gas pressure pushing back on this is going to increase, and my power of my pump is going to have to work harder to push this in there. Exactly the same thing for this electric field that is being created inside the capacitor. Does everyone see that? So if I was going to look at this, I think this is a mechanical analog of a capacitor. If I was going to look at that, what would the pressure look like as I start filling this up over a period of time? I would have a graph that looked like this, right? The pressure would start off as almost zero. But then as it got up there, it would start to increase, wouldn't it? In fact, actually, it would be a linear. That would be a linear one. Well, with volume, to push that in, volume's going to, it would depend on how it would really depend on how I'm pumping that in there. The volume, the pressure, well, it's, you know, the volume in a bottle like this would decrease linearly. So this would be a linear relationship. So, but whatever, you get the analog. I'm going to just cross that out. But you get the analog that I'm doing. As we take more and more electrons from this side, right? We're depleting the electrons on this side. And we're pumping more and more electrons into this side. Eventually, we're going to reach a level where there are no more free conduction electrons that we can take out of the copper that we have here and create an electric field. All right? So that's when the current goes down to 0. We get an open circuit, and the voltage goes up to a maximum, which is going to be the 50 volts. All right? That is capacitors. I went on a little long talking about the theoretical underpinnings of capacitors, but it's very important that you understand that no electrons ever cross the dielectric of a capacitor. That it's just depleting the electrons here that make it seem like there's a short circuit current, and I'm increasing the electrons on the other side, which also makes it seem like there's a current, right? So by depleting these and the electrons going this way, it makes a current that looks like it's going that way. For the electrons going this way, right, it makes it look like there's a current flowing this way. And there is. I mean, as long as electrons are moving, that's a current. So in the beginning, when I first throw that switch, the current acts just like a short circuit current. There is no electrons that are actually going over the capacitor, but the capacitor is depleting electrons on the positive side, and it's adding electrons to the negative side. So it's creating an electric field across that capacitor, and eventually it gets to a maximum where we cannot get any more electrons going either way. We've got the maximum electric field that we can establish there. And that's when we reach these two plateaus. I equals 0, open circuit. V across the capacitor equals 50 volts. All right? Does everyone see how that works? The next lecture, I'm going to talk about inductors. And inductors are not like capacitors. Inductors don't store energy in an electric field. Inductors store energy in a magnetic field. And the current does flow. Okay, on to inductors. See you at the next lecture.